The worst-case scenario sounds like science fiction until you look at the numbers. What if 3I Atlas is not simply passing through? What if its speed, its chemistry, and its silence are not accidents of nature, but signatures of something more? Tonight, we'll walk slowly through the evidence, through the shadows of speculation, and into the unsettling thought. The danger of 3I Atlas may never have been collision, but revelation. When Atlas in Chile caught a point of light that shouldn't exist, the night sky above Chile was as clear as it ever gets. On July 1st, 2025, the automated survey telescopes of the Asteroid Terrestrial Impact Last Alert System, known simply as ATLAS, were carrying out their usual routine. Every 30 seconds, their wide-field cameras captured images of the heavens, scanning for faint streaks or unusual movements. The purpose of the system was simple, even humble: to find rocks that could one day collide with Earth. Most nights were uneventful. Thousands of images passed through the algorithms, most of them filled with stars, galaxies, and known solar system objects. Occasionally, the software flagged an asteroid or a faint comet, usually just another data point in an ever-growing catalog. But in the early hours of July honest, one of those faint specks behaved in a way no catalog could predict. It appeared first as a smudge of light in the constellation Lynx, unremarkable at a glance. Yet its motion against the star field was all wrong. Instead of gliding slowly, as a main-belt asteroid might, it shifted its position by nearly 3 arcseconds per hour. To the Atlas computers, this wasn't just fast, it was too fast. No ordinary object in the outer solar system should move like that. The automated pipeline flagged the detection, and within minutes the data was being checked by human eyes. Astronomers knew immediately that this was something worth a closer look. By dawn, messages were already being exchanged with Pan-STARRS in Hawaii and the Zwicky Transient Facility in California. Within 6 hours, all 3 observatories had confirmed it. A new object already inside the orbit of Jupiter, closing in on the inner solar system at extraordinary velocity. At first, some suspected a mistake. Could this be an artifact, a cosmic ray streak on the sensor, or a piece of space debris in low Earth orbit? But the cross-confirmations ruled that out. This was real. This was distant. And its orbit, once the calculations came in, was not like anything bound to our Sunday. The numbers told the story. Its orbital eccentricity was well above 1, the mathematical signature of a hyperbolic trajectory. In other words, the object was not captured by our star's gravity. It had come from outside the solar system, and after a brief passage, it would leave forever. For a moment, there was awe. Humanity had only ever witnessed 2 such interstellar visitors before: Oumuamua in 2017 and Borisov in 2019. Both had reshaped our understanding of what the galaxy could send drifting our way. Now, against the odds, a third had arrived. It would be named 3I Atlas, the 3I, marking it as the third interstellar object, and Atlas, honoring the telescope system that first caught sight of it. But awe quickly turned to unease. The speed was extreme, nearly 130, 0 miles per hour, relative to the Sunday. Faster than Oumuamua, faster than Borisov, faster than any recorded visitor in astronomical history. To put this in perspective, a rifle bullet might travel at 500 miles per hour. 3I Atlas was moving nearly 100 times faster, and, unlike most comets, this one was already showing a faint coma, a halo of gas and dust at distances where it shouldn't. That was the moment when the ordinary routine of sky surveys gave way to something historic. A faint dot of light, captured in Chile, had just rewritten the night. What followed was a flurry of coordination. NASA, the European Space Agency, and observatories worldwide scrambled to adjust their schedules. Instruments like the Hubble Space Telescope, the James Webb Space Telescope, and arrays of radio dishes began lining up for a closer look. For the first time in 6 years, humanity had a new messenger from the stars, and no one knew yet what message it carried. The discovery of 3I Atlas began as a flicker on a computer screen, a speck of light among millions. But on that night in Chile, it was already clear. This was no ordinary comet. It was a question, written in starlight, that would haunt astronomers for the months to come. Why its orbit proved it came from another star. When astronomers talk about orbits, they speak in the language of eccentricity, a single number that describes the shape of a path through space. A perfect circle has an eccentricity of 0. Most planets, with their slightly stretched ovals, measure just above that. Ellipses dominate our solar system, from Mercury's tighter oval to Pluto's long sweep around the Sunday. Even the wildest comets, flung from the Oort cloud, still return eventually, their eccentricities just below 1. But on July 1st, 2025, when the orbit of the newly detected object was calculated, the number that emerged was not less than 1. It was not equal to 1. It was well above 1. This single fact changed everything. An eccentricity greater than 1 means that the orbit is not closed. It does not circle back. It is hyperbolic, the mathematical curve of something that passes by once and never returns. To be hyperbolic is to be free, to break from the gravitational embrace of the Sun and continue outward into interstellar space. 3I Atlas was not a long-period comet looping in from the Oort cloud. It was not a stray asteroid perturbed by Jupiter's pull. Its path made only one statement: I do not belong here. For astronomers, this realization carried a strange mixture of excitement and unease. Excitement, because this meant a rare chance to study material from another star system. Unease, because such objects are not supposed to arrive often, and yet here was the third in less than a decade. The numbers were precise. Perihelion, the point of closest approach to the Sun, was predicted for late October 2025. Its hyperbolic excess velocity, the speed it would carry even after escaping the Sun's pull, was measured at 61 kilometers per second. This was not a visitor that could ever be captured. It would thread through the solar system and vanish into the darkness, carrying its secrets with it. To visualize this, imagine standing at a vast cosmic roundabout. The planets all trace their circles, endlessly looping. Most comets and asteroids join in, bound by the same rules. But a hyperbolic traveler is the car that does not exit, does not circle. It speeds straight through, crossing the lanes, never slowing, never returning. That was 3I Atlas. The hyperbolic orbit also revealed something deeper, an origin beyond the Sun's sphere of influence. Every object born in our solar system is tied to the Sun, however faintly. Even distant Oort cloud comets, drifting for billions of years, remain bound by gravity. To reach a hyperbolic trajectory, an object must be either ejected violently by a gravitational encounter, or it must come from outside altogether. In the case of 3I Atlas, the velocity was too high for a solar system origin. There was no plausible chain of interactions that could fling it outward at such speed. The only explanation was that it arrived already moving fast, carrying momentum from a distant stellar nursery. This is why the discovery mattered so much. An eccentricity above 1 is more than a number. It is a passport stamp, proof of an alien birthplace. 3I Atlas was not just a comet. It was a fragment of another world, another sun, another story in the galaxy's long history. And yet, even as this fact reassured scientists that it posed no impact risk, its path would never intersect Earth. It also introduced unsettling questions. Why was it so active, outgassing at distances where comets should sleep? Why was it brighter, faster, stranger than expected? And if interstellar visitors arrive more often than we once believed, what does that mean about the galaxy around us? The hyperbolic signature was both answer and mystery. Answer, because it told us with certainty, this object came from beyond. Mystery, because it forced us to ask, why here, why now, and what hidden story carried it across the stars? For centuries, humanity looked up and assumed the solar system was a closed stage, the planets and comets playing their endless roles around the Sunday. On July 2025, that illusion was broken again. 3I Atlas, by its orbit alone, reminded us that the universe is open, that our sky is not bounded, and that sometimes the stars send visitors we never expected. The transformation from C 2025, none, to 3I Atlas. At first, it was barely more than a blemish on a digital image, a single faint blur against the dense star fields of the constellation Lynx. Astronomers at the Atlas telescope in Chile had seen such things countless times before, cosmic smudges that usually turned out to be nothing special. An asteroid wandering through the main belt, a dormant comet briefly reflecting the sun's light, or, occasionally, a trick of the detector itself. But this smudge was different. In the hours after its discovery on July 2025, the speck was assigned a provisional designation, C 2025, none Atlas. The naming convention was routine, clinical even. The C marked it as a cometary candidate. 2025 noted the year of discovery. None indicated the half-month period when it was found, and Atlas gave credit to the survey that first recorded it. At this stage, it was simply one more entry in a long list of icy bodies. Yet, almost immediately, the data began to resist the ordinary. Orbital calculations refined over the following nights showed the object's eccentricity was not less than 1, but well above it. This was no periodic comet, no returning traveler bound to the Sunday. It was unbound, hyperbolic, a drifter from the stars. That single realization was enough to elevate the smudge into something extraordinary, as confirmation poured in from Pan-STARRS in Hawaii and the Zwicky Transient Facility in California. The Minor Planet Center updated its records. The provisional label C 2025, none, no longer seemed adequate. This was not just another comet. This was an interstellar object, the third ever confirmed. And so a new name was assigned, 3I Atlas. The 3I marked it as the third interstellar discovery, following 1I Oumuamua in 2017 and 2I Borisov in 2019. Atlas remained in the name as a nod to the telescope that first spotted it, a reminder of the quiet machines scanning the skies while most of the world slept. With a new name came a new weight of meaning. What had begun as a faint blur on a detector had now entered the history of astronomy. The first interstellar object, Oumuamua, had been a riddle of shape and motion, elongated like no asteroid we had seen. The second, Borisov, was more familiar, a comet in both appearance and behavior, though its chemistry hinted at alien origins. Now, 3I Atlas arrived to complicate the picture further, brighter, faster, stranger still. The transition from C 2025 none to 3I Atlas was more than a change of catalog entry. It marked the moment when scientists realized they were no longer studying a body of this solar system. They were peering at a fragment of another. Every photon of light, reflected from its coma, carried with it the history of a distant nursery, a different star, perhaps a planetary system that no longer even exists. And yet, the sense of wonder was accompanied by an edge of unease. If 3 interstellar visitors had appeared within just 8 years, what did that say about the galaxy? Were such travelers far more common than we believed? Or was their sudden arrival a coincidence loaded with meaning? The smudge had transformed into a visitor. The visitor had transformed into a messenger. And in its new name, 3I Atlas, was written the larger truth, that humanity was now in direct contact, however briefly, with the deep and ancient history of the Milky Way. Every name is a story. C. 2025 None was the story of a discovery, cold and procedural. 3I Atlas became the story of a milestone, our third recorded handshake with the stars. And, like the two before it, this one would leave us with more questions than answers. Speed in space is a relative thing. Our planet orbits the Sun at about 67.0 miles per hour. Mercury, closest to the Sun, races along at nearly 107.0. Even the swiftest asteroids we know rarely exceed those figures. Against this cosmic backdrop, the velocity of 3I Atlas is nothing short of astonishing. When its orbit was first plotted in July 2025, astronomers calculated its heliocentric speed, its motion relative to the Sun, at nearly 130.0 miles per hour. That translates to about 209.0 kilometers per hour, or more than 36 miles every second. To put this into human terms, at that pace, 3I Atlas could cross the entire continental United States in less than 3 minutes. It could travel from Earth to the Moon in just over 2 hours. But speed in astronomy is not simply spectacle. It is also a clue. Every object in our solar system is locked into motion by the gravity of the Sunday. The further from the Sun an object resides, the slower it moves. The closer it falls inward, the faster it travels. Yet, even at its maximum, solar gravity alone cannot account for what was measured here. 130.0 miles per hour is far beyond the typical range of bound solar system objects. The numbers left only one conclusion. 3I Atlas carried with it momentum from somewhere else, momentum it had preserved through millions, perhaps billions, of years of drifting between stars. This speed alone is one of the key proofs that 3I Atlas is interstellar. For comparison, the first visitor, Oumuamua, moved at about 59.0 miles per hour. The second, Borisov, traveled faster still, near 100.0 miles per hour. But 3I Atlas shattered both records. It arrived like a bullet, fired not from within our own cosmic neighborhood, but from a gun barrel aimed across the galaxy. Astronomers call this velocity hyperbolic excess speed, the speed an object retains even after accounting for the Sun's pull. In other words, even if every force of gravity in the solar system tried to slow it down, 3I Atlas would still depart at tens of kilometers per second, unstoppable, uncaptured, gone forever. Its energy is too great, its trajectory too steep. Gravity can bend its path, but never hold it. For those watching from Earth, this raised profound questions. How had such an object gained so much velocity? One answer lies in stellar dynamics. In young planetary systems, as giant planets form, their immense gravity can sling smaller icy bodies outward. Most are ejected only to drift quietly through interstellar space, their speeds modest relative to the galaxy. But a few are thrown harder, faster, by close encounters with massive giants or even binary stars. 3I Atlas may have been such a castaway, accelerated in a gravitational slingshot ages ago, and sent hurtling on a voyage it has been following ever since. Yet another interpretation lingered in the minds of some. What if the speed was not entirely natural? After all, Oumuamua had already sparked debate about possible non-gravitational forces, tiny accelerations that could not be explained by outgassing alone. 3I Atlas, with its sheer velocity, pushed that speculation further. Was this truly just a fragment of ice and rock, or was it a vehicle, its trajectory a disguise, its speed a choice? NASA, of course, remained cautious. Official statements emphasized that 3I Atlas was a comet, remarkable but natural. Still, for the public, the number 130, 0 mph, resonated in a different way. It was not simply fast. It was alien fast. It was a reminder that the galaxy is full of objects moving with energies and histories we barely understand. And so the smudge that became a visitor also became a lesson in humility. The speed of 3I Atlas is not just a statistic, it is a message. The universe is vast, violent, and filled with travelers whose journeys dwarf our own. This object, crossing our skies at impossible pace, is a fragment of that truth. And before long, it will be gone, slipping back into the interstellar night, faster than anything we have ever known. Why orbital mechanics guarantee this object will never come back? Every orbit tells a story. The planets write their tales in near-perfect circles, repeating endlessly around the Sunday. Comets and asteroids trace more elongated loops, some taking decades, others millennia, but all eventually return to the star that binds them. Even the most distant Oort cloud wanderers, drifting for billions of years, remain tethered by gravity's invisible leash. But 3I Atlas is different. Its path is not a loop, but a crossing, a line that cuts through our solar system once, then vanishes forever. Its trajectory is hyperbolic, and that single fact means it carries no return ticket. Astronomers describe orbits with the language of conic sections: circles, ellipses, parabolas, and hyperbolas. Everything bound to the Sun follows a circle or an ellipse, however stretched. A parabola, with eccentricity equal to 1, represents the knife-edge case, a comet just barely escaping, slowed infinitely as it drifts into darkness. But an object with eccentricity greater than 1 belongs to the realm of the hyperbola. Its energy is too high, its momentum too great. It will not slow to a stop. It will not turn back. It will depart into the interstellar deep. For 3I Atlas, the calculated orbital eccentricity exceeds 1.3, far beyond the threshold of escape. Even when the Sun's gravity bends its path, it cannot capture it. Instead, the Sun acts like a stone in a river, deflecting the current but never stopping its flow. 3I Atlas sweeps in, loops around, and shoots outward, its velocity diminished slightly by gravitational drag but still overwhelmingly positive. In plain terms, this visitor is just passing through. The numbers make this impossible to ignore. At its closest approach, or perihelion, in late October 2025, 3I Atlas will skim inside the orbits of Earth and Mars, heated by sunlight, its ices boiling into a bright coma. But by December, it will already be receding, farther and fainter with each passing day. By spring of 2026, it will be beyond Jupiter, and within just 2 years of its discovery, it will fade beyond the reach of even our most powerful telescopes. Its hyperbolic excess velocity, the speed it carries even after escaping the Sun's pull, will remain around 61 kilometers per second, or 136 miles per hour. That figure is the ticket home, written into the mathematics of celestial mechanics. Even if every planet, every gravitational body in the solar system worked together, they could not slow it enough to bind it. The object is free, and freedom means farewell. This is why scientists know, with absolute certainty, that 3I Atlas poses no impact risk to Earth. Its orbit is steep, its trajectory already mapped. There is no hidden curve that could bring it crashing toward us. The same calculations that prove its alien origin also prove its harmlessness. It will not strike. It will not linger. It will not circle back. And yet, this certainty carries its own sting, because what it also means is that our chance to study 3I Atlas is fleeting. We have only months of optimal viewing, only brief windows when it is not lost in the Sun's glare, only a handful of opportunities before it fades forever. This is the paradox. We have been given a visitor from another star, a messenger carrying the chemistry of an alien nursery, but we are allowed only the briefest conversation before it is gone. In that sense, no return ticket is not only a description of the orbit, it is a reminder of the fragility of knowledge. We may never see 3I Atlas again. We may never confirm the mysteries it hints at, its strange chemistry, its unusual coma, its breathtaking speed. Once it leaves, its secrets leave with it. So we watch, we measure, we record, because in the mechanics of the universe, some visitors are destined only to pass once, to brush against our awareness and vanish. And 3I Atlas is one of them. A traveler without a return ticket. A story we are allowed to glimpse only briefly, before it continues its journey into the endless night between the stars. A teardrop coma, both familiar and alien. 3 weeks after its discovery, on July 21, 2025, the Hubble Space Telescope turned its unblinking eye toward 3I Atlas. From its perch in low Earth orbit, Hubble had spent decades watching galaxies form, mapping dark matter and capturing the deaths of stars. Yet now it was asked to do something far more intimate. Study a faint visitor moving swiftly across the starfields of our own solar system. The image that emerged was both ordinary and extraordinary. At first glance, 3I Atlas looked like many comets Hubble had observed before. A bright central point wrapped in a diffuse glow, a cloud of gas and dust expanding outward as sunlight warmed the icy surface. But look closer, and the details told a stranger story. The coma, the faint, gaseous envelope surrounding the nucleus, was unusually compact, almost symmetrical, more like a teardrop than the fan-shaped tails astronomers had expected. Its geometry defied easy classification. Instead of the dramatic sweep of material blown backward by solar radiation, the halo around 3I Atlas looked tightly bound, as though it were reluctant to let go of its own breath. Even more puzzling was what Hubble could not see. The nucleus itself, the solid core of rock and ice, remained hidden within the haze. Astronomers could place only an upper limit on its size, no more than about 3.5 miles across, perhaps as small as half a kilometer. To put that in perspective, this entire object could be smaller than a city, yet it was generating a cloud of gas stretching thousands of miles into space. The scale of activity seemed wildly disproportionate to its size. Hubble's long exposures revealed another detail. The stars in the background appeared as streaks of light, while the comet itself remained sharp and centered. This was the result of tracking 3I Atlas directly as it moved across the sky. In doing so, the telescope had created an image that looked almost like a painting. The comet standing still, the cosmos sliding past in blurred lines, as though time itself bent around the visitor. But there was a deeper mystery hidden in the faint details of the coma. The dust distribution was not smooth. Subtle variations in brightness suggested that gas was not venting evenly from the nucleus, but in jets, specific regions bursting into activity, while others stayed quiet. This hinted at a surface that was not uniform, but patchy. Each vent carrying the memory of conditions that shaped it in another solar system. And then came the missing tail. By theory, solar radiation should have blown dust and gas backward, forming a long anti-solar tail. But Hubble saw almost nothing. The feature was faint, nearly invisible, as though the comet were playing a trick of geometry, hiding its trail from view. Only later, with help from ground-based telescopes, would astronomers confirm that the tail was there, after all, thin, subtle, reluctant to reveal itself. The result was unsettling. Here was an object that behaved like a comet, and yet not like any comet we had seen. Its coma was brighter than expected. Its nucleus was hidden. Its tail was nearly absent. Everything familiar about it came with a twist, as though nature had chosen to remind us that our models were incomplete. For many astronomers, these first Hubble images carried a quiet weight. This was not simply another data point. This was the first detailed portrait of a world that had traveled light years to reach us. It had endured the radiation of interstellar space, survived near absolute zero temperatures, and carried within its dust and ice the chemistry of a distant nursery. And now, for a fleeting moment, it was suspended in our skies, framed by the delicate optics of a telescope orbiting 340 miles above Earth. The teardrop coma of 3I Atlas was familiar enough to be recognized, alien enough to remain unsettling. It was as if the cosmos had handed us a mirror, one that reflected not certainty, but humility. The more we saw, the less we understood why the nucleus has never been directly resolved. At the heart of every comet lies a secret. Beneath the glow of dust and gas, beyond the reach of even our most powerful optics, there sits a nucleus, the true body of the traveler. For ordinary comets within our solar system, that nucleus has often been measured, even imaged in detail by spacecraft flybys. But for 3I Atlas, the third interstellar visitor in human history, the core remains hidden. It is a mystery wrapped in vapor, concealed within its own activity. When the Hubble Space Telescope first turned toward 3I Atlas in July 2025, astronomers hoped to pin down its size. The coma, the glowing shroud of gas, was visible, but the nucleus itself was unresolved. The object appeared only as a bright point embedded in its own haze. Hubble's optics allowed scientists to place an upper limit. The solid core was no larger than about 3.5 miles, or 5.6 kilometers across. It might be far smaller, perhaps only a few hundred meters. The uncertainty was staggering. Was 3I Atlas a mountain-sized relic, or something closer to the scale of a city block? The problem is not instrumentation, but physics. As 3I Atlas approached the inner solar system, solar radiation began to sublimate its ices. Water, carbon dioxide, and other frozen volatiles transformed directly into gas, dragging streams of dust along with them. This material expanded outward, forming a bright coma thousands of miles wide, a luminous fog that overwhelmed any attempt to isolate the nucleus. The very process that made 3I Atlas visible from Earth also cloaked its true form from view. Astronomers have faced this challenge before. Even within our solar system, comets like Hale-Bopp and Hyakutake presented glowing shells that obscured their centers. But spacecraft encounters such as the Rosetta mission at Comet 67P, Churyumov-Gerasimenko, showed us what lay beneath. Irregular, jagged chunks of ice and rock, blackened by cosmic radiation, venting gas in jets. With 3I Atlas, however, no probe can be sent. Its speed is too great, its stay too brief. We are left only with indirect inference, building a picture of the nucleus from shadows in the light. Photometry, the study of brightness over time, offered one possible avenue. Most small bodies rotate, tumbling slowly as they travel. Their reflected light waxes and wanes with each spin, producing measurable fluctuations, a light curve that reveals shape and rotation period. Yet 3I Atlas defied this expectation. Its brightness remained eerily stable, showing none of the periodic flickers astronomers had hoped for. Either the nucleus spins extremely slowly, or its surface is unusually uniform, reflecting light in ways that conceal variation. Both explanations are unusual. Spectroscopy added another layer of intrigue. JWST detected carbon dioxide outgassing at unprecedented levels, yet the faint signature of water vapor remained muted. This imbalance could mean that the outer layers of the nucleus are dominated by CO2, or that a crust has sealed off deeper water ice. Either way, the surface of the core, whatever its size, appears chemically unlike typical solar system comets. It is an alien geology locked away beneath a glowing veil. In the end, the hidden nucleus of 3I Atlas serves as both frustration and symbol. Frustration, because we may never know its true dimensions or shape. Symbol, because the concealment reminds us of the limits of observation. We can measure its coma, trace its orbit, and analyze its chemistry. But the solid heart of the traveler remains unseen, like the beating pulse of another world, wrapped in secrecy. Perhaps that is fitting. 3I Atlas is not a permanent resident of our skies. It is a passerby, a messenger from a place we cannot visit. To demand that it reveal every detail would be to miss the deeper lesson, that sometimes the universe shows us only hints, leaving the rest to imagination. The hidden core of 3I Atlas is not absence, but presence in disguise. It is a reminder that even with the sharpest eyes in orbit, some truths remain veiled, waiting for a future we may never see. Gemini South's confirmation of a faint anti-solar plume. For centuries, comets have been recognized by their most iconic feature, the tail. It is the visible emblem of a body in motion, swept by sunlight and carried by the solar wind. Some tails stretch across the sky for millions of kilometers, bright enough to be seen with the naked eye, etched into memory and myth. But when 3I Atlas first appeared in July 2025, astronomers noticed something troubling. There was no tail. The Hubble Space Telescope had revealed a compact coma, a teardrop-shaped cloud of gas and dust, but the expected anti-solar tail, a plume pointing directly away from the sun, was strangely absent. Instead of a luminous streamer cutting across the sky, there was only a faint, ambiguous glow. This silence, where a comet's voice should have been, puzzled astronomers deeply. The absence of a visible tail raised questions. Was 3I Atlas truly comet-like at all? Was it possible that this was an icy asteroid, venting just enough to create a coma, but not enough to generate a proper plume? Or had geometry conspired to hide it? The tail angled in such a way that Earth's telescopes were looking almost directly along its length, compressing it into near invisibility. Weeks passed, and the debate grew. Then, in late August 2025, the Gemini South Telescope in Chile delivered an answer. Using deep imaging techniques, astronomers finally captured evidence of a faint, thread-like extension stretching away from the nucleus. It was not bold or dramatic like the tales of Hale-Bopp or Neowise, but it was real. A thin, anti-solar plume, whispering against the darkness, confirmed that 3I Atlas was indeed behaving like a comet, though on its own terms. Why was the tail so difficult to see? The leading theory points to the size of the dust grains released. In most comets, small particles dominate, easily pushed outward by solar radiation, scattering light into a spectacular fan. But if 3I Atlas was shedding larger, heavier grains, radiation pressure would have less effect. The tail would form, but it would be narrow, dense, and muted, requiring sensitive instruments to detect. Another possibility lay in geometry. From Earth's perspective, the line of sight may have compressed the structure, making a three-dimensional plume appear like a faint blur. It was as though the comet had hidden its most recognizable feature behind an optical illusion. Yet, the discovery raised deeper questions. Why would an interstellar comet behave so differently from local examples? Was its surface so altered by millions of years in deep space that only certain ices remained active? Did cosmic radiation bake it into a crust that vented reluctantly, expelling dust in unusual ways? Or was this simply a reminder of diversity, that comets are not a single class, but a family of wanderers, each shaped by different histories? For astronomers, Gemini South's detection was more than a technical achievement. It was a reassurance. The tail, however faint, confirmed that 3I Atlas shared kinship with the comets of our solar system. It vented, it shed, it responded to the Sunday. It was alien, yes, but still subject to the same universal physics that guide all icy bodies. And yet, the faintness itself carried meaning. Where we expected spectacle, we found subtlety. Where we anticipated a blazing banner across the stars, we discovered a whisper, a signature so slight that only the most patient instruments could reveal it. The cosmos, it seemed, had chosen to remind us that not all truths are obvious. Some require quiet searching. In the end, the hidden tail of 3I Atlas became symbolic. It was a feature both present and absent, real yet reluctant, visible only when sought with care. It reminded us that even when patterns hold, when comets behave as comets should, the details can surprise, defy, and humble. The anti-solar plume may not light up the night sky. It may never be remembered by casual stargazers. But in the archives of Gemini South, in the delicate stretch of pixels confirming its presence, lies a simple truth. Even across light years of wandering, this visitor carries the same physics, the same fragility, the same whisper of dust and gas that define all comets. Familiar, and yet alien. No periodic flicker, no tumbling spin. Every rotating body in space has a rhythm. Asteroids brighten and dim as their irregular surfaces reflect sunlight unevenly. Comets, with their lopsided nuclei and patchy activity, often flicker like distant lighthouses as they spin. These light curves, subtle fluctuations in brightness measured over hours or days, are one of astronomy's simplest yet most powerful tools for revealing hidden truths. They tell us how fast an object rotates, how elongated its shape might be, and whether it tumbles chaotically or spins in balance. But when astronomers turned their instruments toward 3I Atlas, that rhythm was absent. Throughout July and August 2025, observatories across the world recorded the comet's brightness night after night. Sensitive photometers tracked its light output across long intervals, expecting to see the telltale up and down pattern of rotation. Instead, the measurements came back eerily flat. The brightness of 3I Atlas held steady, unchanging within the limits of detection. At first, some thought this was an artifact. Perhaps the coma, the glowing envelope of gas and dust, was simply too bright, masking the subtle flicker of the nucleus beneath. Indeed, comet often blur out small variations, but the consistency of the flat line raised deeper questions. Even with the coma's interference, most comets betray some rhythm, however faint. 3I Atlas did not. There were only two main possibilities. The first was that the nucleus rotates extraordinarily slowly, so slowly that its surface features never revealed themselves across the weeks of observation. A rotation period, measured in days or even weeks, could produce a near-constant light curve. If true, this would make 3I Atlas one of the slowest rotators ever recorded. The second possibility was stranger still, that the nucleus's shape and surface reflectivity were unusually uniform. If it were nearly spherical, with no elongated edges to catch light unevenly, and if its surface activity were evenly distributed, then its spin might leave little trace in brightness. But comets are rarely uniform. They are messy, jagged relics, scarred by impacts and fractured by heating. To imagine one so smooth and balanced stretched credibility. Speculation grew. Could interstellar radiation over billions of years have sanded 3I Atlas into symmetry, grinding away irregularities until only a rounded survivor remained? Or was the coma itself not a natural veil at all, but something more deliberate, an engineered disguise that erased rotational signatures, hiding the object's true form from distant observers? Astronomers are cautious with such leaps. The simplest explanation remains the slow rotator hypothesis. Yet even this carries implications. A comet that spins too slowly risks uneven heating. One hemisphere could be baked by the sun while the other remains frozen. Such asymmetry could fracture the nucleus, tearing it apart as internal stresses build. If 3I Atlas is truly such a body, then its survival across interstellar space is even more remarkable. The flat light curve became a symbol of the object's enigma, while Oumuamua's flickering brightness suggested a tumbling, cigar-shaped rock, and Borisov's variations revealed a classic cometary spin. 3I Atlas offered nothing but stillness, a calm line where chaos was expected. For scientists, the silence of the light curve was both frustrating and profound. It left them with fewer clues, but also with a sense of awe. Perhaps the object's steadiness was not an absence of information, but information in itself, a statement about resilience, about survival, about the diversity of forms that wander between the stars. And for those who lean into speculation, the calmness whispered something else, that what hides its spin might also hide its nature. In the end, 3I Atlas did not blink, did not tumble, did not reveal a rhythm. It moved through our instruments like a ghost, steady, unwavering, as though it had carried its stillness across light years. A smudge of light with no pulse, no flicker, no heartbeat, yet full of mysteries waiting in the silence. Goldstone's strange specular reflections. In late August 2025, as 3I Atlas approached its perihelion, astronomers sought not only to see it, but to hear its echo. Optical telescopes capture light, spectrographs read chemistry, but radar can reveal shape, surface, and motion in a different way. By bouncing radio waves off an object and analyzing the returning signal, scientists can peer through the coma and glimpse hints of the hidden core. It is a method that has mapped asteroids, measured the spins of distant moons, and tracked comets racing past Earth. The Goldstone Solar System radar in California, a dish nearly 70 meters wide, was tasked with the experiment. Its transmitters sent pulses of radio energy across millions of kilometers of space, aimed at the tiny, moving speck that was 3I Atlas. Minutes later, faint whispers of those pulses returned. The echoes were weak, almost drowned in cosmic static, but they carried clues. What the radar revealed was unexpected. Instead of the diffuse scatter usually returned by rough cometary surfaces, the signal contained bright, specular reflections, spikes of energy consistent with radio waves bouncing off smooth, mirror-like regions. Natural comets, with their rugged, dusty crusts, rarely act like polished metal. Their echoes are typically grainy, spread out, and uneven. Yet here, amid the noise, were reflections as sharp as glass. The finding puzzled the team. One possibility was that parts of 3I Atlas's nucleus were coated in unusually smooth ice, preserved across billions of years of interstellar wandering. If sunlight had not fractured its surface as violently as in typical comets, some regions might remain glistening, like frozen panes in the dark. Another explanation pointed to large dust grains surrounding the nucleus. Clumps of coarse material could, in certain alignments, reflect radar cleanly, producing the illusion of smoothness where none exists. But the most provocative thought lingered on the edges of the conversation. Specular reflections are also the signature of technology: solar panels, metallic hulls, engineered structures. To imagine such things inside the glow of 3I Atlas was to venture into speculation, but the radar data gave fuel to the imagination. A comet behaving like a mirror was not easily dismissed. Still, the discipline of science requires caution. Goldstone's observations were brief, limited by the faintness of the target and the noise of the environment. The echoes did not provide an image, only hints. The balance of evidence still supported a natural explanation, even if unusual. Smooth ices, consolidated crusts, or peculiar dust dynamics could all account for the effect. The extraordinary claim that an interstellar visitor might be artificial remained unproven, as it always had with Oumuamua and Borisov. Yet, the mirror-like echoes captured a deeper truth about the way we see. When we study objects so faint, so far, every signal is a riddle. We interpret shadows of shadows, leaning on mathematics and probability. And sometimes, those shadows align in ways that suggest something stranger than we expect. For 3i Atlas, the Goldstone reflections became part of its growing mythology. First a smudge, then a hyperbolic traveler, then a comet with a hidden tail, a still light curve, and now an object that, in radar, glinted like polished glass. Each layer added complexity. Each new instrument saw something both familiar and alien. In the end, the radar results did not prove 3i Atlas to be more than a comet, but they did remind us of the limits of certainty. To stand at a dish on Earth, transmit pulses into the void, and hear them return from a body that began its journey around another star, this in itself is extraordinary. The strangeness of the echo may not be evidence of technology. It may only be evidence of diversity, of the endless ways matter arranges itself across the galaxy. Still, the phrase lingers. Radar like a mirror. A comet that should scatter light instead reflects it cleanly. Familiar physics, but with an alien twist. Another reminder that every time we think we know what to expect, the cosmos chooses to surprise us. JWST finds CO2 outnumbering water 8-1. In early August 2025, the James Webb Space Telescope turned its instruments toward 3i Atlas. Unlike Hubble, which captures light in visible and ultraviolet wavelengths, JWST specializes in the infrared, the subtle glow of heat, where molecules reveal themselves through their fingerprints. With its powerful spectrographs, Webb can decode what an object is made of, molecule by molecule. By splitting its light into precise patterns, the expectation was simple. Comets in our solar system, when heated by the sun, usually vent a mixture dominated by water vapor, with lesser amounts of carbon dioxide and carbon monoxide. Water ice is abundant, and when it sublimates, it drives much of the comet's activity. In most cases, carbon dioxide is present but secondary, a quiet partner in the chemistry of cometary comets. But what JWST found in 3i Atlas was no ordinary chemistry. Its spectrum was dominated by carbon dioxide at a ratio of nearly 8-1 compared to water. This was not just unusual, it was unprecedented. Out of thousands of comets observed in our solar system, none had ever displayed such an imbalance. Where scientists expected to see the familiar fingerprint of water, they found instead the overwhelming presence of CO2. The discovery sent ripples through the astronomical community. How could such a composition arise? Several theories were proposed. One suggestion was that 3i Atlas had formed in the outer regions of its birth system, beyond the so-called CO2 snow line, where temperatures were so cold that carbon dioxide froze out more readily than water. In this scenario, the comet would be fundamentally different from our own, carrying the frozen memory of a stellar nursery, unlike the Sun's. Another idea was that cosmic radiation during its long interstellar journey had altered the balance. Over billions of years, high-energy particles might have reshaped its surface, driving off water while leaving carbon dioxide trapped beneath, until heating by the sun released it in dramatic bursts. A third possibility involved the buildup of a dust mantle, a crust insulating deeper ices, preventing water from escaping while allowing more volatile CO2 to leak through pores. Each explanation was plausible, yet none felt complete. The sheer dominance of carbon dioxide suggested something more than an edge case. It forced scientists to ask whether 3i Atlas might represent an entirely different category of icy body alien, not only in origin but in fundamental chemistry. The implications were unsettling. If interstellar comets carry such diverse compositions, then the galaxy's planetary nurseries may produce worlds under conditions far stranger than our models predict. Our assumptions, built on the small sample of comets born around the Sun, may be deeply incomplete. 3I Atlas, in this view, was not just an outlier but a messenger, showing us that the diversity of planetary chemistry is broader than we imagined. And yet, there was another whisper at the edges of speculation. Some asked, what if such chemical ratios were not natural at all? Could the overwhelming presence of CO2 be more than a relic of formation? Could it be a signal, an engineered signature? After all, carbon dioxide dominates industrial processes on Earth, from combustion to manufacturing. Was it too far-fetched to imagine that chemistry itself might carry information, a code written in molecular abundance? Officially, the scientific consensus remained cautious. Natural explanations came first, speculation second. But the unease lingered. A comet that glowed with carbon dioxide, 8 times stronger than water, was unlike anything we had seen. It was familiar, and yet alien. The carbon dioxide shock of 3I Atlas was not only a chemical puzzle, it was a challenge to our assumptions. It reminded us that when we stare at a spectrum, we are not just reading molecules. We are glimpsing the history of another world, another star, another time. And sometimes, what we see forces us to admit how little we know. Conflicting signals about hydration. For comets, water is destiny. In our solar system, nearly every comet observed has been dominated by water ice, its sublimation driving the coma and tail that make these objects so striking. Water vapor is the heartbeat of cometary activity, a fingerprint as familiar to astronomers as oxygen is to life on Earth. But with 3I Atlas, the script was turned upside down. When the James Webb Space Telescope recorded its spectrum in August 2025, it revealed an astonishing imbalance. Carbon dioxide outnumbered water by nearly 8-to-1. For many, this immediately raised the most basic question: where is the water? Other instruments complicated the picture. Ground-based telescopes equipped with sensitive near-infrared spectrographs hinted at traces of water vapor, but far less than expected for a comet so close to the Sunday. Radio observatories, searching for the 22 GHz emission line that normally betrays water molecules, reported silence. The combined dataset looked contradictory, faint hints in some places, near absence in others. There were several possible explanations. The most conservative suggested that water ice was still present, but hidden beneath a thick dust mantle. Over billions of years in interstellar space, cosmic rays may have processed the surface into a dark, carbon-rich crust. This layer could act as insulation, sealing water beneath while allowing more volatile carbon dioxide to seep through cracks. If true, stronger water emissions might emerge later, as 3I Atlas drew closer to the Sun and solar heating penetrated deeper. Another explanation involved its place of birth. If 3I Atlas formed in the cold outer zones of its natal system, beyond the water snow line, it might have accreted less water ice to begin with. Instead, its bulk composition could be dominated by carbon dioxide and carbon monoxide, making its current chemistry not an anomaly, but a reflection of its true origin. Yet the mystery persisted, because even comets formed in the cold should typically show more water than this. For a body showing so much activity to have so little H2O in its spectrum felt almost paradoxical. Some astronomers turned to more speculative ideas. Could the apparent absence of water be an observational illusion? The coma, dense with carbon dioxide, might be masking the weaker water signal. Or, alternatively, the water vapor could have been lost long ago, stripped away by cosmic radiation during its long exile between the stars, leaving behind only the more volatile compounds locked in deeper reservoirs. A few push the boundary further. If one were to imagine an engineered object masquerading as a comet, then deliberately suppressing the water signature might be one way to hide. On Earth, water is ubiquitous in life and in planetary formation. An interstellar visitor, lacking it so dramatically seemed, to some, like a fingerprint, whether of alien geology or something stranger. NASA, ESA, and the Minor Planet Center remained cautious. In press briefings, they emphasized the need for continued monitoring. "Absence of evidence is not evidence of absence," one astronomer remarked, noting that deeper layers might still reveal water as perihelion approached. But the phrase, "Where is the water?" echoed quietly in the halls of observatories worldwide. In the bigger picture, this puzzle touched something profound. Water, the substance we consider essential to life, was simply not where we expected it. For decades, scientists assumed that icy wanderers from other systems would look broadly similar to our own, frozen archives of water, carbon, dust, and organics. 3I Atlas broke that assumption. It reminded us that the chemistry of other stars, other planets, other comets may be far stranger than our models allow. Perhaps the water is there, waiting to reveal itself in the weeks before closest approach, or perhaps it was never there to begin with. Either way, the mystery lingers. 3I Atlas, the visitor from another star, has left us with a haunting question, one that cuts to the heart of our search for kinship in the cosmos. If even comets do not carry water as we expect, then how different, how alien, might the rest of the galaxy truly be? CO2 clouds extending hundreds of thousands of kilometers. When astronomers describe comets, they often emphasize how fragile and faint these objects are. A nucleus only a few kilometers across can nevertheless generate a coma, a halo of gas and dust, stretching thousands, sometimes millions, of kilometers. Sunlight heats the surface, sublimating ices into vapor, which expands outward and reflects light, creating the glowing shrouds we associate with comets. But with 3I Atlas, even this familiar process played out in ways that defied expectation. By August 2025, telescopes worldwide began reporting that the coma of 3I Atlas was already immense, extending hundreds of thousands of kilometers into space. This was surprising not only for its size, but for the distance from the Sun at which it was detected. Most comets begin serious outgassing when they are near the inner solar system, typically within 2 astronomical units of the sunday. But at more than 3 AU away still beyond Mars, 3I Atlas was already venting strongly, producing a coma as if it were far closer. The James Webb Space Telescope confirmed the culprit: carbon dioxide. Unlike water, which requires relatively high temperatures to sublimate, CO2 begins to vaporize much farther out. In 3I Atlas, carbon dioxide was not just a supporting player, it was the dominant force. The result was a coma inflated to extremes, a gaseous balloon surrounding a nucleus still hidden from view. This raised important questions about the object's structure. How could a body so small maintain such activity? Was the nucleus unusually rich in volatile ices, stored from the cold nursery where it formed? Or was something else feeding the coma something deeper, perhaps even mechanical? Some astronomers speculated that the energy source seemed disproportionate to the size estimates of the nucleus. A body no larger than a mountain was producing an atmosphere the size of a planet. The sheer size of the coma also made observations challenging. For ground-based telescopes, the faint outer edges were difficult to distinguish from background starlight. Only with careful processing could astronomers trace its full reach. JWST's infrared sensitivity, however, cut through the glare, revealing CO2 bands glowing strongly in the cold dark. The scale was breathtaking. A cloud so wide that Earth itself could fit inside it dozens of times over. In some ways, the coma was reassuring. It confirmed that 3I Atlas was indeed a comet, behaving in accordance with physical laws. Gas sublimates, pressure builds, vapor expands, and a halo forms. But the details were unsettling. The dominance of CO2, the absence of water, The enormous size at such distance all combined to paint a picture that did not quite fit our models. And then came the speculative whispers. Could such an overgrown coma serve a purpose beyond natural venting? A natural coma diffuses outward, dispersing quickly. But if engineered, if managed, it could act as camouflage, scattering signals, obscuring what lies within. Radar attempts, after all, had returned mirror-like echoes. Light curve studies had failed to reveal rotation. What if the coma itself was part of the disguise, a cloak deliberately maintained to keep the nucleus hidden? The official position remained cautious. Most astronomers agreed that extreme CO2 activity could be explained by formation conditions and interstellar weathering. Still, the sheer size of the coma stood as one of the great puzzles of 3I Atlas. For the casual observer, the coma would never appear in the night sky. Unlike comets like Hale-Bopp, this visitor would not dazzle with naked-eye brilliance. Its brightness, spread thin across a vast halo, remained a treasure for telescopes only. Yet within that faint glow lay a message. The overgrown coma of 3I Atlas was both a spectacle and a warning, a reminder that even familiar processes can produce alien results when carried across the gulfs of interstellar space, and a symbol of how much we still do not know. What this chemistry suggests about its birth system. Every comet is a time capsule. Within its ices are locked the conditions of the place where it first formed, the temperature, the density of gas, the balance of molecules in a young planetary system. Studying our own comets has revealed how the solar system was built: water from the outer disk, organics from further out, and dust that has circled the sun since before Earth itself existed. But 3I Atlas is not one of ours. It carries the frozen memory of another nursery, another star, and its chemistry, dominated by carbon dioxide, forces us to imagine a birthplace very different from the sun's domain. In our solar system, the snow lines of the early disk played a crucial role. Close to the sun, only metals and silicates could condense. Farther out, water could freeze, marking the water snow line. Still farther, carbon dioxide and carbon monoxide froze out, creating layers of icy diversity. Most comets we see today formed just beyond the water snow line, in regions where H2O ice was abundant. That is why their comae are dominated by water vapor, with CO2 and CO playing secondary roles. But for 3I Atlas, the ratios are reversed. The James Webb Space Telescope showed carbon dioxide outnumbering water 8-1. This suggests a nursery colder, darker, and perhaps more chaotic than our own, a place where water ice was scarce, and carbon dioxide was the primary building block of frozen bodies. One possibility is that 3I Atlas formed near the CO2 snow line of its natal star system. If that star was cooler or dimmer than the sun, perhaps a red dwarf, then the region where carbon dioxide could condense would have been closer in and richer in icy material. The comet we see today might be a survivor from such a disk, shaped in a chemistry we rarely encounter. Another possibility is that 3I Atlas formed in a giant unstable disk where violent gravitational interactions scattered material outward. In this case, its composition could be the product of mixing. Dust from warmer zones coated with CO2-rich ices from colder regions. If so, the comet represents not a simple, uniform fragment, but a hybrid record of a turbulent young system. Its long interstellar journey complicates the story further. For billions of years it wandered in the void, bombarded by cosmic rays, altered by radiation, slowly reshaped. Over such spans of time, water ice might be sputtered away, while carbon dioxide, trapped in deeper layers, remained to be released when sunlight struck again. If true, what we see today is not only the fingerprint of its birth, but the scar of its exile. And yet, some scientists entertain another thought. If interstellar comets, like 3I Atlas, consistently show unusual chemistries, Perhaps our solar system is the outlier. Perhaps water-dominated comets are not the rule, but the exception. If most nurseries produce CO2-rich wanderers, then our understanding of planet formation must expand. It would mean that alien worlds formed from disks, unlike our own, may carry atmospheres and oceans shaped by chemistry we find unfamiliar. Speculation lingers, too, in quieter corners. Could such chemistry be intentional? If an advanced civilization sought to seed the galaxy with probes disguised as comets, altering the balance of volatiles might be one way to make them stand out or to hide them among the natural diversity of icy bodies. It is a thought experiment more than a conclusion, but one that whispers at the edges of discovery. Whatever the truth, 3i Atlas reminds us of a simple fact. Every comet is a storyteller, but this one speaks with an accent not of our world. Its chemistry points back across light years, to a nursery we cannot see, a star we may never find, and in its frozen breath is the memory of an alien beginning one that, for a brief moment, has drifted close enough for us to glimpse. Could ratios themselves be a signature? Science often teaches us to look for patterns. In astronomy, patterns of light and chemistry tell us what stars are made of, what planets may exist, and how galaxies evolve. Yet, occasionally, a pattern emerges that feels less like natural order and more like a message. For some researchers observing 3i Atlas, the extraordinary dominance of carbon dioxide over water raised an unsettling question. Could the ratios themselves be intentional? The James Webb Space Telescope measured CO2 emissions nearly 8 times stronger than water vapor. In solar system comets, water is nearly always dominant, with CO2 and CO acting as minor contributors. But in 3i Atlas, the script was flipped completely. For a natural explanation, astronomers proposed cold birth environments, radiation processing, or buried water layers sealed by dust. All were plausible, yet none erased the strangeness of the ratio itself. This is where the so-called industrial hypothesis enters a thought experiment rather than a conclusion. It asks, what if molecular ratios could serve as signals, markers, or even codes? On Earth, after all, our own atmosphere now carries chemical fingerprints of industrial activity. Elevated carbon dioxide, methane spikes, nitrogen oxides. Were an alien astronomer to study Earth's spectrum from afar, they might notice imbalances that hint not only at biology, but at technology. Could 3i Atlas represent a similar phenomenon in reverse? A chemical fingerprint that looks unnatural precisely because it is? Proponents of this line of speculation argue that an 8-to-1 ratio is more than a statistical quirk. It is sharp, emphatic, difficult to explain through ordinary models of cometary evolution. If such ratios appear consistently across multiple interstellar visitors, one might begin to suspect a pattern. And patterns, in the history of science, are often the first whisper of deeper truths. Skeptics counter with caution. Extraordinary claims require extraordinary evidence, and so far, 3i Atlas provides only one data point. Outliers happen. Some comets in our own solar system show unusual chemistry like C, 2016 R2, with its odd mix of carbon monoxide and nitrogen, but no one claims they are artificial. Diversity, not design, may be the better explanation. Yet the industrial hypothesis remains valuable, even if only as a lens. It forces astronomers to sharpen the distinction between what is natural and what might be engineered. If a truly artificial object were to arrive, what markers would we expect? A perfectly smooth light curve? A radar echo like a mirror? Or perhaps, most subtle of all, a chemical balance that cannot be reconciled with natural formation. Some even extend the thought further. Imagine a civilization seeding the galaxy with probes disguised as comets, each carrying a chemical tag encoded in its outgassing. To the casual observer, they would be ordinary icy bodies. To those with spectrographs sensitive enough to decode them, they would be messages, ratios as language, molecules as script. Of course, mainstream science emphasizes restraint. The best explanations for 3I Atlas's CO2 dominance remain natural: formation in an alien nursery, radiation altering the balance, or an insulating crust hiding water. Still, the discomfort lingers. Why is the chemistry so extreme? And why does it feel as though the object is telling us something we cannot quite read? The industrial hypothesis may never move beyond speculation, but its very existence reveals how 3I Atlas has stretched our thinking. This visitor from another star has already expanded the boundaries of what we consider possible, and in doing so, it reminds us of the thin line between discovery and imagination. Perhaps the ratios are nothing more than chemistry, frozen in an alien nursery billions of years ago, or perhaps in ways we have not yet learned to decipher. They are signatures written not by accident, but by intention. In either case, 3I Atlas forces us to look at the universe not only with instruments, but with questions as old as wonder itself. What is natural and what is not? 270 million kilometers, nearly twice Earth-Mars distance. When a comet approaches the inner solar system, the question most people ask is simple: how close will it get? For centuries, tales of fiery omens in the sky have stirred fear of collision. But with 3I Atlas, the numbers provide immediate comfort. This interstellar visitor will come no nearer than 270 million kilometers, roughly 1.8 astronomical units, or nearly twice the distance between Earth and Mars at their closest approach. To understand why this matters, consider scale. The Moon orbits Earth at just 384, 0 kilometers away, a distance so small by cosmic standards that we can measure it with lasers. Mars, at its closest, can approach Earth by about 55 million kilometers. But 3I Atlas, its path will keep it nearly 5 times farther than Mars ever gets, and hundreds of times farther than our Moon. At such distances, there is no physical threat. It is not a bullet aimed at Earth, but a traveler threading a line that barely grazes the outer lanes of our neighborhood. And yet, closest approach is still significant. For astronomers, December 2025 will mark the brief window when 3I Atlas shines brightest, when its coma and faint tail can be studied with the greatest clarity before it recedes back into the dark. Even at 270 million kilometers, the comet will only reach magnitude 11, far too faint for the naked eye. But just within reach of amateur telescopes under dark skies. For professionals, it is the moment when every instrument, from Hubble and JWST to the vast radio arrays of Earth, will be aimed at the wanderer, gathering as much data as possible before the chance is lost. The safe distance also underscores a crucial point about orbital mechanics. 3I Atlas follows a hyperbolic trajectory. This means that while it will swing around the Sun, its speed ensures it cannot be captured. The same mathematics that guarantee its interstellar origin also guarantee its harmlessness. Its closest pass is not a flirtation with danger, but the natural consequence of geometry, an angled path through our system, bent but not bound by the Sun's gravity. Still, the idea of a visitor so close yet so far carries a certain bittersweetness. At 270 million kilometers, 3I Atlas remains beyond any possibility of spacecraft interception. Had we known sooner, perhaps a mission could have been launched, a probe sent to meet it, as we once did with Comet 67P. But the discovery came only months before its arrival, leaving no time to prepare. The closest approach is, in this sense, a missed opportunity. We must observe from afar, straining our instruments to catch whispers from a world we cannot touch. For the public, the numbers may feel abstract. 270 million kilometers is difficult to imagine, but it is also reassuring. It means there will be no fiery streak across the atmosphere, no apocalyptic scenario. Unlike the cinematic fears of rogue comets, this one passes quietly, almost politely, a messenger who keeps a respectful distance. And yet, in the speculative shadows, some ask, what if distance does not matter? If 3I Atlas were more than a comet, if it carried technologies beyond our imagining, would 270 million kilometers truly be safe? Could surveillance, observation, or signals bridge that gap? The worst-case scenario may not involve impact at all, but contact at a distance, unnoticed except by those who know how to look. Still, the mathematics are clear, the trajectory precise, the conclusion inescapable. 3I Atlas will pass, and it will pass far away. It will leave no scars on Earth, no debris in our skies. What it will leave is memory of the moment when an alien fragment swept near, close enough to study but too distant to grasp. Closest approach is not danger, it is gift. A fleeting chance to look into the chemistry of another world, to watch a messenger from beyond glide past, and to remember that in the vast emptiness of space, even 270 million kilometers is close enough to feel like an encounter. Why, orbital mechanics declare it harmless. When news of a comet or asteroid discovery reaches the public, a familiar question rises almost immediately. Is it going to hit us? The fear is understandable. Humanity has inherited a collective memory of impacts, the extinction of the dinosaurs, Tunguska in Siberia, Chelyabinsk in Russia. The cosmos has scarred our planet before, and it will again. So whenever a new object enters the spotlight, reassurance depends on more than words. It depends on numbers. With 3I Atlas, the numbers came quickly. Its hyperbolic orbit was calculated within days of its discovery in July 2025. Using hundreds of observations, astronomers refined the parameters: inclination, eccentricity, perihelion distance. The eccentricity, at over 1.3, was the first clear signal it was not bound to the Sunday. The object would enter, loop, and exit, never to return. The second comfort lay in the minimum orbital intersection distance, MOID, the closest the path of 3I Atlas would ever come to Earth's orbit. That number was not a few thousand kilometers, nor even a few million. It was hundreds of millions. At 270 million kilometers, its closest approach is nearly twice the Earth-Mars minimum distance. In celestial terms, that is a gulf as wide as certainty allows. These calculations are not guesses. They rely on Newton's and Einstein's physics, tested across centuries. By plugging in positions, velocities, and gravitational influences, astronomers can project an orbit forward with astonishing accuracy. The mathematics that guides spacecraft to distant planets is the same mathematics that guarantees safety from 3I Atlas. For those who still feel unease, consider this. Even if every known source of uncertainty were magnified, if hidden jets of gas nudged the comet, if dust outbursts altered its spin, the trajectory would not shift enough to change the conclusion. At most, such effects alter a path by thousands or tens of thousands of kilometers. But when the separation is hundreds of millions, the numbers stand immovable. This is why astronomers speak with confidence. The phrase "no impact risk" is not hopeful language. It is the direct consequence of geometry. 3I Atlas is fast, but it is also distant. It slices through the solar system on a line angled well away from Earth. Gravity bends its course, but only enough to carry it back outward. It is, quite literally, on a one-way ticket home to the stars, and yet the reassurance carries a touch of irony. For while the public is comforted by safety, scientists feel a quiet frustration. If the object were closer, if its MOID were smaller, we might have had a chance to launch a mission, to study it up close. But safety, in this case, means inaccessibility. The very geometry that declares Earth unharmed also declares us powerless to do more than watch from afar. Still, the comfort is real. Unlike the hypothetical planet killers that haunt doomsday scenarios, 3I Atlas is no threat. Its danger lies not in collision, but in mystery. The numbers tell us it will not strike, but they cannot tell us what secrets it carries. Perhaps that is the true lesson of orbital mechanics. The calculations give us peace of mind. They prove that, physically, we are safe. But they also remind us that knowledge has limits. Numbers protect us from fear of impact, yet they cannot protect us from the larger questions. Where did this visitor come from? What does its chemistry mean? And are there more like it on the way? For now, we take comfort in certainty. 3I Atlas will not harm Earth. The mathematics leaves no room for doubt. The sky, for all its mysteries, is safe this time. How language calms a nervous public. Whenever a celestial visitor makes headlines, a familiar rhythm plays out. Astronomers publish their data, journalists translate the findings, and the public reacts with a mixture of awe and unease. A body from another star sounds mysterious, even ominous. And so, alongside the numbers that prove 3I Atlas harmless, there is something just as important: the language used to explain it. NASA, more than any other agency, understands this balance. Over decades of planetary defense work, its teams have learned that public trust depends not only on precision, but on tone. The public wants facts, but they also want reassurance, and reassurance is crafted in words. In the days after 3I Atlas's discovery, NASA's press releases carried phrases that seemed carefully chosen. The object was described as passing safely, its orbit well understood, its trajectory non-threatening. These words are not accidents. They are selected to diffuse anxiety before it grows. For many readers, the mathematics of orbital eccentricity, or hyperbolic excess velocity, means little. But the sentence, "no risk to Earth," is clear. This approach reflects a long history. When Oumuamua was discovered in 2017, speculation about alien technology ran wild. NASA responded with calm statements, framing it as a natural object until proven otherwise. When asteroid Apophis briefly raised fears of impact in the 2000s, NASA consistently reminded the public that improved measurements had ruled out danger. The goal is always the same: to keep wonder alive while extinguishing panic. With 3I Atlas, the challenge was doubled. Not only was it fast and alien, it also carried chemical surprises: carbon dioxide dominating over water, mirror-like radar echoes, and a faint, reluctant tail. Each new discovery fed the sense of strangeness. For a public primed by movies about rogue comets and interstellar threats, the imagination easily ran ahead of the data. NASA's language had to anchor that imagination. So, in press briefings, scientists emphasized scale: 270 million kilometers at closest approach. They repeated certainty: its orbit is hyperbolic, meaning it will not return. They leaned on comparisons. It will remain nearly twice as far as Mars ever comes to Earth. These phrases do more than convey numbers. They convert abstractions into comfort. At the same time, the tone is careful not to dismiss curiosity. Astronomers acknowledge the mystery. They speak of the chance to study alien chemistry, to test theories of planetary formation, to expand our sense of the galaxy. By highlighting the scientific value, they redirect anxiety into fascination. Instead of fearing 3I Atlas, the public is invited to feel proud that human instruments can study it at all. This balance between caution and wonder, between calm and excitement, is central to NASA's role. Too much emphasis on danger could spark panic. Too little could breed suspicion that risks are being hidden. By speaking with quiet certainty, the agency builds trust. And yet, behind the scenes, scientists are as intrigued as anyone. They know the data is strange, that 3i Atlas does not fit neatly into categories. But they also know that the worst-case scenario is not impact, but misunderstanding. A public that loses faith in science may fear every discovery. A public reassured may continue to support the telescopes and missions that make discovery possible. Thus, NASA's words become part of the event itself. The object travels through space, but its meaning travels through language. A comet that will never touch Earth still touches us through the way it is described. In the end, NASA's reassurance is more than comfort. It is a reminder that science is not just equations, it is communication. And as 3i Atlas sails past, what lingers is not fear, but a calm voice saying, "We are watching, we understand, and you are safe." To understand 3i Atlas, it helps to remember that it is not the first of its kind. Twice before, our solar system has been visited by wanderers from beyond. Each left behind questions, debates, and a sense of awe. Taken together, they form a trilogy of encounters: Oumuamua in 2017, Borisov in 2019, and now 3i Atlas in 2025. The first, Oumuamua, arrived unexpectedly. Detected by Pan-STARRS in Hawaii, it was small, faint, and fast, an elongated shard of rock tumbling through space at nearly 60 miles per hour. Its brightness flickered dramatically, suggesting a shape unlike any asteroid or comet we had seen. Stranger still, it showed a non-gravitational acceleration, a tiny push away from the sun that could not be fully explained by outgassing. Some scientists suggested it was a fragment of a disrupted planetesimal. Others dared to ask if it might be artificial, a solar sail, perhaps, drifting between the stars. No consensus was reached. Oumuamua left us with a mystery more than a memory. The second visitor, 2i Borisov, discovered by amateur astronomer Gennady Borisov in Ukraine, was different. Unlike Oumuamua, Borisov looked and behaved like a textbook comet. It sported a bright tail, vented familiar molecules, and resembled the comets of our own solar system, though with subtle chemical twists. It was larger than Oumuamua, easier to study, and less controversial in nature. Where Oumuamua had unsettled us with strangeness, Borisov comforted us with familiarity. It showed that interstellar objects could look very much like what we already knew. Then came 3i Atlas, which in some ways seems to sit between the two. Like Borisov, it displays a coma and a tail faint but real. It is visibly cometary, venting gases under solar heat. Yet, like Oumuamua, it also defies expectations. Its chemistry is alien. Carbon dioxide outshining water at unprecedented levels. Its light curve is oddly calm, showing no spin. Its radar echoes glint like polished surfaces. In this sense, 3i Atlas combines the strangeness of Oumuamua with the cometary character of Borisov, complicating the story further rather than resolving it. Comparing the three highlights just how little we know. 3 visitors in 8 years might sound like abundance, but in statistical terms, it is still a vanishingly small sample. Each could be an outlier, or each could represent a broader category of objects drifting through interstellar space. We simply do not yet know. The contrasts also raise questions about planetary formation in other star systems. If Oumuamua was rocky, Borisov icy, and 3i Atlas rich in carbon dioxide, then perhaps interstellar objects reflect the diversity of environments where planets are born. Some nurseries produce elongated shards, others frozen comets, others volatile-rich hybrids. In this way, each interstellar visitor is like a fragment of a different language, a syllable of a larger story we are only beginning to translate. And yet, Comparison brings perspective too. Oumuamua frightened some because it was so unfamiliar. Borisov reassured because it was so ordinary. 3i Atlas does both at once familiar in outline, alien in detail. It reminds us that discovery is rarely a straight line from question to answer. More often, each answer only deepens the questions. What connects all three is transience. Oumuamua is gone. Borisov is gone. Soon, 3i Atlas will also fade into the interstellar night. They come briefly, uninvited, leaving just enough behind to unsettle our certainties. Perhaps the most important context they provide is not in their differences, but in what they share. They are visitors who remind us that the galaxy is not empty. It is filled with fragments, messengers, and mysteries, drifting silently until chance brings them to our door. Why the chance of collision is mathematically zero. Whenever a new celestial object is discovered, one question always rises above the rest. Could it hit us? It is a question rooted in memory of dinosaurs wiped out by a cosmic rock, of impact craters that scar Earth and the Moon. Hollywood films have only amplified the anxiety, painting comets and asteroids as existential threats waiting to fall from the sky. So, when astronomers announced that 3i Atlas was on its way, many asked the same question. The answer, this time, was simple and absolute. The probability of collision is zero. Why such certainty? The explanation begins with orbital mechanics. Every object in space obeys the laws first outlined by Kepler and Newton, later refined by Einstein's relativity. With a handful of observations, precise positions measured against background stars, astronomers can calculate the path of an object with astonishing accuracy. For 3i Atlas, those measurements quickly revealed a hyperbolic orbit. Its eccentricity was greater than 1, meaning it is not bound to the Sunday. It will sweep in, bend around, and depart forever. But more importantly, its trajectory misses Earth by a wide margin. At closest approach in December 2025, 3i Atlas will remain about 270 million kilometers away. To put that in perspective, that is nearly twice the minimum distance between Earth and Mars. It is hundreds of times farther than the Moon. Even if the orbit were adjusted by thousands of kilometers, a huge shift in astronomical terms, the margin of safety would remain vast. Mathematically, this margin leaves no room for impact. Orbital calculations include uncertainty, windows, ranges of possible positions due to measurement limits, or small, non-gravitational forces like outgassing. But in the case of 3i Atlas, the uncertainties are tiny compared to the scale of separation. Even the most extreme scenarios keep it far from Earth. This is why scientists can say with confidence that the collision probability is not just low, it is effectively zero. Some might wonder whether unseen forces could alter its course. Comets can indeed change slightly as jets of gas erupt from their surfaces, nudging them off predicted paths. But the effect is minor. Outgassing can shift a trajectory by a few thousand kilometers over months, not by hundreds of millions. No conceivable cometary activity could bend 3i Atlas onto a collision path. Its immense speed, about 130, 0 miles per hour, makes it even less susceptible. At that velocity, small forces have negligible influence. This clarity stands in contrast to near-Earth asteroids, where predictions sometimes leave a sliver of uncertainty. Objects that pass within a few tens of thousands of kilometers may carry probabilities of impact measured in fractions of a percent, refined away only after more observations. But 3i Atlas is not a near-Earth object. It is a passerby on a hyperbolic arc, so distant that even the language of probability becomes unnecessary. Its chance of collision is not 1 in 10, 0, or 1 in a million. It is 0. For scientists, this certainty is liberating. Instead of worrying about planetary defense scenarios, they can focus entirely on the science, its chemistry, its light curve, its mysteries. For the public, it offers reassurance. The interstellar visitor may be strange, alien, and fleeting, but it is not dangerous. And perhaps there is symbolism in that. 3i Atlas reminds us that not every messenger from the stars carries threat. Some carry only questions, mysteries, and the promise of discovery. Its hyperbolic path guarantees departure. Its vast distance guarantees safety. In the ledger of cosmic risks, it does not even appear. So, while the imagination often leaps to catastrophe, the numbers provide comfort. The laws of motion declare, unequivocally, that 3i Atlas will never strike Earth. Its impact on our world will be intellectual, not physical, a shift in how we see the galaxy, not a scar on the ground. And in that sense, the probability of collision may be zero, but the probability of wonder is infinite. From the beginning, one fact about 3i Atlas has been repeated with certainty. It will not stay. Its orbit is hyperbolic, its velocity too great, its fate sealed as a one-time visitor. But what if that assumption is wrong? What if the very speed we use as proof of its interstellar nature is not what it seems? Could hyperbolic motion itself be camouflage? The idea sounds like science fiction, yet the debate is worth exploring because it reveals both the strengths and limits of our understanding. When astronomers measured 3i Atlas's velocity about 130, 0 miles per hour relative to the Sun, they concluded it was unbound. At such speed, even the Sun's gravity cannot hold it. That is why it has been catalogued as 3i, the third interstellar object. But what if that speed were not purely natural? Suppose, for argument's sake, that the trajectory were being managed. A spacecraft designed to mimic a comet could adopt a hyperbolic arc deliberately, using its speed as a disguise. To astronomers, it would appear as just another interstellar visitor, destined to leave. But if such an object carried the ability to alter its course, later slowing down, hiding within the solar system, its initial hyperbolic motion would have masked its true intent. Is there evidence for this? Not directly. No deviations from the predicted orbit have yet been observed. Radar echoes, faint though they are, align with a small, natural nucleus. The coma and tail, while unusual in chemistry, still follow physical laws. Yet the very strangeness of its signals, the CO2 dominance, the faint tail, the mirror-like radar reflections, invites speculation. Could the anomalies we explain as quirks of geology instead be hints of something more deliberate? In fairness, science offers natural explanations. Gravitational slingshots in its home system could have given 3i Atlas its excess velocity. Billions of years in interstellar space could have stripped water, leaving carbon dioxide to dominate. A crust could hide the nucleus, muting light curve variations. Each puzzle has a plausible answer without invoking design. Still, the what-if lingers. It lingers because Oumuamua, too, left us uneasy with its unexplained acceleration. It lingers because Borisov, though more ordinary, was still unlike any comet we had seen. And now, with 3i Atlas, we face another visitor whose chemistry and behavior stretch our models. How many anomalies must pile up before imagination takes hold? If hyperbolic speed were camouflage, the strategy would be elegant. Astronomers assume that hyperbolic orbits guarantee departure. They calculate impact risks, declare them zero, and relax. Few continue to watch after the comet fades, because there is no expectation of return. In that sense, the disguise is built into our trust of orbital mechanics itself. A masquerade hidden in mathematics. Of course, there is no evidence that 3i Atlas will stay. Its path matches the equations. Its course is consistent with natural forces. Most likely, it will depart as expected, vanishing into the interstellar dark. But speculation has value. It reminds us that certainty is often contextual. We know what the equations predict, but we must also admit how much we do not know about objects from other stars. So, could hyperbolic speed be camouflage? Perhaps not in this case, but the question itself opens our minds. It forces us to imagine how a truly advanced probe might hide, how signals could be mistaken for natural variation, how assumptions might blind us. 3I Atlas is almost certainly just what it appears to be, an icy fragment from a distant nursery. Yet, by asking what if it stays, we stretch our vision. We acknowledge the line between science and imagination, and we remember that both have roles to play when we confront the unknown. One of the most remarkable features of comets is their ability to move under their own chemistry. As ices heat and turn to gas, they erupt from vents, creating jets of sublimation that act like natural thrusters. Over time, these tiny pushes alter the orbit of a comet in subtle but measurable ways. For ordinary comets, this is an annoyance to orbital calculators, but not a mystery. Outgassing explains the changes. But what if the same process could be mimicked deliberately? What if what looks like natural sublimation is, in fact, propulsion in disguise? This speculation has shadowed every interstellar visitor since Oumuamua. That first object, after all, showed an unexplained acceleration that scientists struggled to reconcile with natural models. Some suggested thin sheets of ice venting invisibly, while others whispered about solar sails. With 3I Atlas, the possibility arises again. Its coma is vast, its tail faint, its chemistry strange. Could sublimation itself be more than geology? Could it be machinery masked as nature? Consider how subtle such camouflage could be. If an advanced probe were wrapped in volatile ices, it could release gas in controlled patterns, each vent serving as a miniature thruster. To telescopes, the activity would appear indistinguishable from a comet, plumes of carbon dioxide, dust streaming outward, a halo of light. Yet, beneath the performance, hidden systems might be adjusting trajectory, guiding the object not on a passive path, but on an intentional one. The anomalies of 3I Atlas feed this line of thought. The overwhelming dominance of CO2 over water could be natural, but it also resembles a design choice, favoring a volatile that vents efficiently at greater distances. Its light curve, unusually calm, could mean a nucleus so smooth and balanced that its spin leaves no trace, or it could mean orientation is being stabilized by artificial means. Even the mirror-like radar echoes invite questions. Natural ice can glint, yes, but specular reflections are also the hallmark of polished surfaces. Science, of course, prefers conservative answers. Sublimation explains the coma. Jets explain any deviations in trajectory. The simplest explanations remain the best. And yet, the idea of hidden systems disguised as sublimation cannot be fully dismissed. Not because evidence demands it, but because imagination insists on asking. If we were to design probes to drift undetected between stars, would we not hide them inside cometary shells? Would we not use natural venting as cover for propulsion? Even natural comets blur the line. The European Space Agency's Rosetta mission to Comet 67P revealed jets bursting from specific vents, reshaping the orbit with every outburst. To an observer from afar, such precise, directed plumes might look engineered. In that sense, any comet is already a machine, a natural one, running on sunlight and frozen fuel. Perhaps the distinction between engine and sublimation is smaller than we think. What matters is that 3I Atlas forces us to confront the possibility. If the venting we see is natural, then we are learning about alien chemistry. If it is not, then we may be staring at a technology disguised in plain sight. In both cases, we are humbled. The safe bet is that 3I Atlas is natural, an icy relic from a distant nursery. But the worst-case scenario, or perhaps the most extraordinary one, is that its coma is not just a veil, but a mask. That hidden systems hum beneath the gas, that engines breathe alongside sublimation, that what we call activity is actually intention. As always, we return to humility. The data show jets of CO2, the interpretation is ours. And in the space between fact and imagination lies the haunting thought. What if those jets are not just physics, but propulsion? What if the engines of another world have come disguised as a comet's breath? No discussion of interstellar visitors is complete without mention of Avi Loeb, the Harvard astronomer who, in 2018, made a bold claim that Oumuamua, the first interstellar object ever detected, might not be natural at all. His argument was simple but daring. The strange acceleration of Oumuamua, combined with its unusual shape and lack of visible outgassing, could be explained if it were a thin, light sail, possibly a probe, drifting through space. The idea was controversial. Many in the scientific community pushed back, insisting that extraordinary claims require extraordinary evidence. They argued for natural explanations. Perhaps hydrogen ice sublimation, perhaps a fragment of a disrupted planet, perhaps geometry playing tricks with light. Yet Loeb's suggestion took hold in the public imagination. For many, the probe hypothesis was irresistible. Now, with the arrival of 3I Atlas, the question has resurfaced. Its behavior is not identical to Oumuamua, but its strangeness is undeniable. Its overgrown coma, dominated by carbon dioxide, its faint, reluctant tail, its unusually calm light curve, and its mirror-like radar echoes all combine to make it feel less like a textbook comet and more like a puzzle. If Oumuamua could be interpreted as a possible probe, why not 3I Atlas? Supporters of the idea point to patterns. Both objects arrived unexpectedly, both carried anomalies, and both were fleeting. In Loeb's framework, interstellar objects might represent a class of artifacts, probes drifting silently, disguised as natural debris, seeding the galaxy with watchers or messengers. The diversity we see, from Oumuamua's rock-like shard to Borisov's icy tail to Atlas's CO2 cloud, could reflect not only natural variety, but multiple strategies of camouflage. Critics, however, urge caution. The chemistry of 3I Atlas, while alien compared to solar system comets, is still explicable within natural physics. A comet forming in a CO2-rich nursery could produce exactly the ratios observed. The faintness of its tail may result from larger dust grains. The still light curve could simply be the coma masking subtle rotations. For many scientists, invoking probes is unnecessary when natural explanations suffice. Still, Loeb's central point was never just about Oumuamua. It was about open-mindedness. He argued that dismissing the possibility of technology out of hand is as unscientific as assuming it without evidence. The responsible approach, he suggested, is to treat each anomaly as a question mark, to follow the data wherever it leads, even if that means entertaining extraordinary scenarios. With 3I Atlas, this philosophy resonates. The probe question may not be answerable, but it frames the way we look. Radar, spectroscopy, light curves, even SETI's radio listening all are sharpened by the awareness that we may be studying more than just geology. The act of asking keeps us vigilant. Of course, extraordinary claims also have risks. If every unusual comet is branded a possible probe, the credibility of astronomy itself could erode. The line between science and speculation must be carefully drawn. Yet, it is also true that history has often punished the dismissal of radical ideas, only to reward them later. The tension between skepticism and imagination defines the frontier of discovery. So, where does 3i Atlas fit? Perhaps it is nothing more than a fragment of ice and rock, shaped in an alien nursery, venting carbon dioxide into the void. Perhaps its anomalies are merely the fingerprints of diversity. Or perhaps, as Loeb once suggested, the probe question deserves to remain on the table not as an answer, but as a reminder that our assumptions may blind us. The truth may never be known. 3i Atlas will soon fade, vanishing into interstellar night. What remains is the legacy of its mystery and the willingness of some to ask whether we are alone. In that sense, the probe question is less about proving aliens and more about keeping wonder alive. The equations promise safety, the telescopes confirm no collision, and yet, the danger of 3i Atlas was never about impact. It was about what it might represent. A mirror held up to our assumptions, a quiet reminder that the universe is stranger than we dare imagine. The worst-case scenario may not be disaster, but discovery and the realization that we were never alone in the dark.